I'm Rick. I am supervised by Eduardo and by David Kubisnak in Charles University. I'm here today to talk to you about a paper that I published last year in Physical Review D. Essentially, there are two topics we're going to talk about here. One is localized non-relativistic quantum systems in curved spacetimes, and I'll explain what I mean by this very soon. And then we're going to apply this to talk about a general characterization of particle detector models, and that's something that many people talk about today. Okay? So what do I mean by the localized non-relativistic quantum systems in curved spacetimes? First, by non-relativistic quantum system here, to me, we will be talking about, oh, it's scrolling down. Oh, it's going to be, I'm sorry? Command 2. Okay, thanks. Thanks. So by non-relativistic quantum system, what I mean here is a system with one position degree of freedom. So it's a wave function, okay? By localized around the trajectory, basically, I'm assuming that there is a potential that strongly localizes the system in space. And now what we want to do is to describe the system, this non-relativistic wave function, in a background curved spacetimes, assuming that it's localized around the trajectory. In order to do this, the mathematical tool we're going to use are the Fermi normal coordinates. So basically, we need to take into account the curvature spacetime, and the Fermi normal coordinates are kind of going to help us do this. What are the Fermi normal coordinates? Basically, these are coordinates that, given a timelike curve, they are such that if an event has coordinates tau and x, then this event lies in the surface labeled by tau. Tau also just so happens to be the proper time of the trajectory. And x here has a physical interpretation because it corresponds to the geodesic distance from the curve to the event, okay? And the only drawback of these coordinates, of course, is that in a general curved spacetime or for general trajectories, they're only defined locally around the trajectory, okay? So that's a feature that they have. And because of this, everything that we're going to talk about here will be restricted to a region where the Fermi normal coordinates are defined. This Fermi bound L here, it's effectively the maximum radius that a system can have in order to be described in Fermi normal coordinates, okay? And you can actually estimate this Fermi bound L in terms of the acceleration of the trajectory. So this is the norm of the proper acceleration, and in terms of the curvature of the induced curvature in the surfaces. Okay, so basically you can estimate this L from below. Now, this is what we're going to need about Fermi normal coordinates. But what we want to talk about is this. We want to be able to talk about a wave function that is localized around an arbitrary trajectory in curved spacetimes. We want to talk about a wave function that's defined in the local spaces, in this local rest spaces associated to these trajectories, okay? So basically, let's assume that we're given a wave function in flat spacetimes. So we're given a wave function psi. You can think of this as an element of the space of square integrable functions. Then we know that with this wave function comes the position operator and the momentum operator. And we can write the Hamiltonian for this particle as a function of this position operator, momentum operator, and possibly an external time parameter t that could control an external potential or something like this. Now, our goal here is to get these things, to adapt them in a way that they make sense around an arbitrary trajectory in curved spacetimes. So basically, we want the wave function to become an element now of the space of square integral functions in the rest space associated to the trajectory for each tau. We want to generalize the position momentum operators somehow, such that these are still self-adjoint operators and such that they satisfy the canonical commutation relations. And we want to adapt the Hamiltonian by incorporating the new dynamics that might come from the fact that the trajectory is moving and that spacetime is curved. So the way to do this is effectively to, well, first we need an inner product for the space of the functions. Given that this space sigma tau, the rest space is coherently defined, it's just a surface, a space-like surface in spacetime, we can just use the induced volume element in this surface sigma tau. This will define an inner product, which is compatible with what we found in the past when we were reducing the Dirac equation to the Schrodinger equation in around the trajectory. So we found that this is actually the inner product that would naturally arise there to leading order and curvature at least, okay? So I'm just like extending this a little bit, ignoring the leading order. And to apply this formalism, of course, now if we're integrating over these surfaces, the wave functions must be localized within the surfaces, right? So there'll be an assumption that the functions are localized within this Fermi radius, within this circle around the trajectory, which has proper distance equal to the Fermi radius of the associated trajectory. Basically, we're assuming that the localization of the system is small enough so that we can approximately describe it in around the trajectory in curved spacetimes. We can relax this assumption by just assuming that the wave functions are approximately Fermi localized instead of being Fermi localized. But basically, we're going to assume that it's very localized around the trajectory. Now, the next step is to talk about the position and momentum operators. So the position operator is simply going to be defined by multiplication by the Fermi normal coordinate position, simply because there's this physical content that the Fermi normal coordinates have, effectively corresponding to the geodesic distance between the center of the curve and the point x. And the momentum operator, it's defined like this, which is basically the minus I partial derivative, but we have to add these factors here so that this momentum operator here is self-adjoint with respect to the inner product of the surfaces, and also so that the canonical commutation relations are satisfied. But if we define this P and this X, they're both self-adjoint operators, and the canonical commutation relations are also satisfied. Okay. So this is for the kinematics. Now for the dynamics of the theory, basically, if we're given this Hamiltonian H that depends on X, P, and T, we want to reinterpret the X and P in the new ways that we just defined, and to replace this external time parameter T by the proper time under the assumption that this Hamiltonian is described by an observer that is undergoing this trajectory here in curved spaces. Okay, so basically we're going to reinterpret the X and the P and replace T by tau. So this is the Hamiltonian. The only extra thing that we have to take into account here is redshift, because each point of these slices here, of these rest spaces, is moving differently in principle with respect to the central trajectory here. In order to accommodate for this, what you do is you include a redshift factor, which can be written in terms of the metric induced in the surfaces and along the trajectory, so in Fermi normal coordinates. And using this redshift factor, we get this Hamiltonian here, which is basically the product of whatever we had before, but now with the redshift factor, right? There are some comments that I could make about this, but I'm not. If you guys want to ask, feel free. But this is not entirely self-adjoint, okay? Because here there's a P and here there's an X, okay? In principle, if you try to check self-adjointness with this would not be self-adjoint. So I have to correct for this. There are ways to correct this. I describe them in the paper. But basically, for us, what matters is that if you solve Schrodinger's equation, and if you assume that the non-relativistic energy of your particle is much smaller than its rest mass, then no matter which way of solving this self-adjointness issue you find, this curly Hamiltonian, which is the Hamiltonian with the redshift factor, will look like exactly the Hamiltonian you used to have, plus these two correction terms. So these are the two correction terms that show up to leading order under the assumption that the non-relativistic energy of your system is much smaller than its rest mass. And we can just call these two terms the H relativistic for relativistic corrections. So we find that basically, after you reinterpret the X, the P, and redefine the kinematics, this is the term that will change the dynamics of your particle because it's in curved spacetimes. Okay. And then important to remember this: the limit of validity of this framework. Basically, we need this system to be more localized than the Fermi bound of the trajectory, which can be estimated by this. And also, we need the non-relativistic energy of the system to be sufficiently smaller than its rest energy. Okay. Under these two assumptions, we can use this formalism to describe this system. Now, I actually developed this because I work with particle detector models, and I wanted to have a more connection between extended particle detector models and systems that we can talk about, such as atoms and things like this. Now, particle detector models are localized non-relativistic quantum systems that interact with quantum fields, okay? So these, we're gonna hear a lot about these. These are useful for probing the Unruh effect, Hawking radiation, for implementing local measurements in quantum field theory, for quantifying the amount of entanglement in quantum field theories. So particle detectors are nice. They're cool. We like them. Okay. And basically, now I want to get the formulas that we have for localized non-relativistic quantum systems and apply these to systems that are interacting with the quantum field. So, and of course, the limits of validity of the formulas for the non-relativistic quantum systems that we just described will also carry on. So we talked a lot about quantum field theory yesterday in the algebraic perspective. This is going to be the most brief introduction to quantum field theory you've ever seen. A quantum field for me phi A, where A here is any collection of Lorentz indices, will be essentially an association of test fields to elements of a star algebra. Okay, so basically, this is the way you should think of the quantum field, is this operator value distribution, right? And you can implement conditions regarding causality, additional properties of the algebra, commutation relations. You can decide to handle gauge. But if you can talk about this operator here, phi A of x, then everything that I'm going to say here applies. Okay. So what is the particle detector that couples to a field operator OB? So B here, any collection of Lorentz indices. This can be like derivatives, the covariant derivative of your field. This could be the partial derivative of your field, could be the stress energy momentum, doesn't really matter, provided that you define it properly. But now the point is, the particle detector couples to this. So the detector is a localized non-relativistic quantum system. They'll be undergoing this trajectory z of time. So exactly what we just talked about. The coupling with the field will be defined by a tensor valued operator mu b. Okay, the mu b is what I'm going to call the generalized monopole moment, and this is an operator in the detector Hilbert space. So basically, this is the operator of the detector that will couple to the field operator OB. In fact, the interaction Hamiltonian will be prescribed like this, whereas here you see the contraction of the generalized monopole moment with the generalized with the operator that the detector couples to. Okay, and here I'm evaluating the operator OB in the position operator of the detector of the localized non-relativistic quantum system. And we also have to include a redshift factor, because again, we are describing this with respect to an observer that is undergoing the trajectory z of tau. Each point of the surfaces will have a different redshift factor. So yeah, you have to include this as well. Now, if you do, what you get is that you can recover most usual detector models in the literature. So in fact, if you assume that your detector has a discrete amount of energy levels, you will see that your interaction Hamiltonian will look like this. If you have already handled particle detector models, this should be kind of familiar. If you didn't, this is how a very general particle detector interaction Hamiltonian looks like. Basically, this omega here is the energy gap between energy levels En and Em. And this lambda here is a space-times mirroring tensor, which is given by the product of the wave functions of the detector with this generalized monopole moment. But this interaction Hamiltonian here, with the suitable choice of space-times mirroring functions and operator that it couples to, can effectively recover, for instance, the real scalar UDW model, which is the simplest particle detector model that we have, or the complex scalar UDW model, or even the light matter interaction. If you consider an atom in curved spacetimes interacting with the electromagnetic field, this can also be recovered by this. Fermionic particle detectors, so nucleons interacting with neutrinos, or quadratically coupled detectors, or even if you want detectors coupled to linearized quantum gravity, it doesn't really matter. Okay, cool. So the last thing that I want to say, actually, is about what are the consequences of these relativistic corrections from the Hamiltonian, right, that we found, that the wave function has. There are two cases. One case is the case in which this h of tau is time independent, so there's no extra time dependence coming from the h-rel, and you can just diagonalize the initial Hamiltonian of your detector, okay? If you can do this, then you just compute the new energy gap and the new wave functions. These will depend on curvature and acceleration. Just define your particle detector model in curved spacetimes. Just probe your quantum field. But in the other case, where h of tau is time dependent, now where these two really depend on the proper time of the trajectory, and you can simply diagonalize this h of tau, what's going to happen is you're going to have to use perturbation theory with both the interaction with the quantum field and the relativistic corrections, right? So if you do this, now essentially acceleration and curvature might blur how much you're going to be able to probe regarding the quantum field. So that's basically it. Sorry that this presentation is kind of rushed. It's kind of hard to present this in with like 15 minutes. But so basically, we developed a framework for describing localized non-relativistic quantum systems in curved spacetimes. We identified the new dynamics introduced by acceleration and curvature spacetime, which are these two terms that you have to add into your description. Now we're talking about a wave function in curved spacetimes to leading order corrections in curvature and acceleration. This framework is valid provided that, one, the system is more localized than the Fermi bound of the trajectory. Two, its non-relativistic energy is sufficiently smaller than its rest mass. And we use this formalism to define a general notion of particle detector model. It's not the most general you can talk about it, because you could still consider a superposition of trajectories, for instance. This is not like described by this formalism. But still, it's a more general notion of particle detector model. And the regimes of validity from the description of the localized non-relativistic quantum systems also impose a regime of validity on these particle detector models. And finally, we discussed how curvature and acceleration affect the dynamics of particle detectors. So thank you very much, and that's it.
Questions?
Yes.
We've got one here, two there.
Hi, thank you very much for the nice talk. I have a question about the operator O relative to the field.
Yeah. It can be...
Yeah, in general, I saw that in a lot of particle detector models present in literature, it is the field operator itself. Am I right? But I wonder, for example, the field operator involves an infinite number of modes, involves an integration of all the momenta. It is possible to consider a field operator which is selecting particular momenta and neglecting the others?
Yes, but you're going to violate microcausality if you do, right? You're going to violate, you're going to get something which is not entirely compatible with relativity if you do that. Because then you'll be getting modes which are localized within a finite region of spacetime, right? And this is going to violate causality a little bit, but you can in principle.
Okay, thank you. I'll think about it.
Okay. Yeah, we can talk more about this later if you want.
More questions there?
Hi, thank you for the talk. So, I mean, the usual problem with having point particles in curved spacetime is, of course, that if you can then introduce a self-interaction, you get into, well, a mathematical mess, essentially. Now, you could normally say in classical situations, okay, well, the energy of my point particle may be negligible. So, but here you need a sufficiently high mass. So
it's not sufficiently high mass. I would say sufficiently small non-relativistic energy, which is the mv squared compared to m. So effectively, I'm saying that the particle, the detector, is a non-relativistic quantum system.
okay.
That's basically the condition there, right? And regarding point particles being problematic, depends on what you mean by point particles. Point-like detectors are definitely not. Point-like detectors don't have any issues. So basically, if instead of considering this interaction Hamiltonian, I just had I didn't have an integral dnx, and I just had an evaluation of the field operator at the trajectory, this would be perfectly well defined and would work. The issue is that this kind of a singular limit, right? Of like say an atom interacting with the field is not really point-like, right? But yeah, that's kind of what motivated me to develop this approach.
Got another question in the back.
Yeah, so thanks for the talk. And as we have seen, somehow this spatial localization of the wave function seems to be very important in the construction Is it easy to see why this kind of thing is not in attention with the Hegerfeld's theorem? So as a reminder, it's a theorem that in a relativistic quantum mechanics, a spatially compactly supported wave function cannot be purely in the positive frequency Hilbert space, from which we get the non-relativistic limit. Yeah. So
yeah, I have a couple of things to say about this. So first, this is all an effective treatment, right? As a matter of fact, it is known that smeared particle detectors do violate causality up to the size of their smearing. Okay, so we do know that for a fact. This is an effective model, which you can use in many situations, not in all of them. You have to check. And second, I'm not using quantum field theory to describe the detector, right? So like the detector is simply like, say, this is like a harmonic oscillator that is like it's a harmonic oscillator with an external potential. As a matter of fact, yeah. So basically, the detector is not described by quantum field theory, so that's why it's not in conflict. But there are other prices that we have to pay because we do that. That's what I have to say.
Okay, so I've got two quick questions, but I think I'm going to ask just one.
Okay.
Which is the inner product that you defined.
Yeah.
Is it independent of tau?
It depends.
Then I don't understand that.
It depends on the trajectory.
Then you are creating probability.
Then I'm sorry?
You are creating probability.
No, it depends. So the thing is, it's an underlying assumption here, which is adiabaticity, which is basically that curvature and acceleration don't vary too much along the.
No, well, I don't really mind that much because it's in the very beginning. You are just defining something that is depending on your evolution. And I'm not talking about the quantum field. I'm just talking about the quantum, the non-relativistic quantum system.
Yes, in the case of the non-relativistic quantum system, this inner product here might depend on time. In principle, in general, it is.
But that does not necessarily mechanics.
No, there are ways of implementing this into this. So basically, what I'm assuming here is that this varies. This inner product here varies small enough, very sufficiently slow, so that this can be compatible with. Because you can formulate quantum mechanics with a time-dependent inner product, but your Hamiltonian will not be self-adjoint. So what I'm assuming here is that this varies in time slowly enough so that my Hamiltonian will be self-adjoint, approximately. That's basically it, yeah.
And the other question is related to that, but I think we're running out of time, so
okay.
Let's start afterwards. With the self-adjoint nature of the operators X and P and that you introduced. Okay. But we can do that later.
Okay, yeah, for sure.